Okay, the paper today. Stable isotope mass spectroscopy analysis of the oldest known assemblage of microfossils document their taxon-correlated carbon isotope composition by Bill Schopf. There's a long history that goes behind this paper. Bill Schopf, long ago, I think in the 80s, discovered some fossils in Western Australia, some of the oldest rocks on the Earth, or things in these rocks that he thought looked like fossils of bacteria. And folks have gone back and forth. If you look at them, you say, yeah, they're bacterial. And if you were to look at them closely and do careful analysis of how they're arranged in the rocks, etc., if these rocks were 300 million years old, they would never be questioned. They're obviously bacterial fossils. But the fact that they're 3.2 billion years old means that's an extraordinary claim, right? And so you need better evidence that it's real. And so he's gone back and forth. People have argued about whether these things are real fossils or not. And although he considers the claim long ago sorted, I think this paper does a really good job of really putting the nail in the coffin that these really are fossil microbes. So what are we looking at? Well, these pictures are terrible. Let's see. So these are sedimentary cherts. They're carboniferous, meaning that these fossils are made of carbon, embedded in silica. And they don't look like much in these pictures. They look much better in better images. There's some nice spirals amongst these, etc. But that carbon, Bill would argue, is the carbon from the actual organism that that's a fossil of, that it is not replacement material. A lot of fossils, the actual material that the animal or creature was made of has been replaced, with stuff like silica or pyrite or whatever. These are carbon, and so could it be that that's the carbon from the original creature? Well, let's go back and think about what kind of environment this was. These are, this environment is complicated. Again, it was 3.2 billion years ago. A lot has happened to that rock in the meantime. These are sands that have been concreted, essentially as sediments, and then the environment was a hydrothermal field after that. And so what you're looking at is veins of a hydrothermal vent with sediment, embedded in the sediment. And these fossils are in the sands of the sediment. So they predate the hydrothermal vent. They're concretes. If you look at the size and the shapes, I wish I had some better pictures. There's some beautiful spirals amongst these fossils. These don't do it justice. Are any of these better? Not really. And so the question is, if this is carbon, if this stuff is carbon from the original creature, we learned already that when creatures fix carbon, they change the isotope ratios that are in that carbon. And so what they did was they used stable isotope mass spectroscopy, essentially a laser that would cut this rock, expose this surface, polish it up really nicely, and then blast it with ions. They use cesium ions to do this. And it would eject carbon ions from the surface, and they can take the mass spectrum of that. And so when they do that, what they find is that they could correlate where's the description? Oh, here we go. Here's some nice pictures. These fossils were long ago divided into, they put names on them. That's a little presumptuous, I think. But they put names on these creatures. And again, they're really careful with these experiments because when you do this experiment, you destroy the fossil. And so you have to be careful doing it. They took the isotope ratios of fossils like this one. They took each morphological class of fossil, and they did several examples, blasting the carbon out, measuring its isotope ratio, and then also taking, this is a low magnification view, so this is a cross-section through this hydrothermal vent system. And so there's a bunch of other carbon in there that isn't associated with fossils, and so they have a control of sorts with that. And they're showing here, these are the blasts, because you leave a divot in the rock when you blast them. And so they divided the fossils into classes and then looked to see what carbon ratios they got. And when they do that, kerogen is the kind of carbon this is. This carbon is completely transformed. It's basically coal. They find 3 different classes and they isotope ratios depending on the morphology of the fossils. And so the morphology of the fossils predicts the carbon isotope ratio. And so you know in advance what it's going to be if you're blasted just by looking at the fossils and looking at the morphology. And when you look at that, what you find is that one morphology has, negative 27 for carbon-13 parts per thousand for the bulk carbon in this hydrothermal field. The particular kerogen, these are less isotope ratioed, or less fractionated. They find that you have 3 classes, and those correspond exactly to modern carbon isotope ratios from methanogens, from methane oxidizers, methanotrophs, and from photosynthesis. And so they can look at these fossils now and say, for example, that this thing is a methanotroph. It's a methane oxidizer. That's pretty powerful. If you can look at a fossil, look at something that you think is a fossil, and predict this carbon ratio, and that carbon ratio predicts a metabolism, that's pretty good evidence that what you have is a real fossil. These are the oldest specific fossils that we know of. Before this, there's evidence for life, but it's in the form of just bulk carbon, weird isotope ratios, and things that look like stromatolites, these layered biofilms embedded in rock. But of course, they're completely transformed and replaced, and so there's arguments about whether those are legitimate or not. But these things, I think, they've shown really are fossil bacteria. And being able to identify what they're doing, or what they were doing 3.4 billion years ago, is pretty spectacular.